Okay, so we'll get into part 2. The very heavy chapter, so just bear with me. Okay, so one lecture is about 2 hours. Oh my gosh. You can pause it and keep going, yeah? Do like about 30 minutes one time. Yep. Or maybe everybody running 10 minutes and put name on it. Yeah, whatever, I have a duty to teach you. Okay, whether you take it or not, it's up to you. Okay, so we're getting into regardless of feature size, which is your secondary and tertiary datum features. So let's go into there. So this is a continuation of our cylinder study. Yeah, we deal with the internal and external. Yeah, then we deal with the diameter. Of course, this is we're talking about the internal and external diameter. It is automatically understood when we talk like that, and because there's an axis in the center. Which is your cylinder. Yeah, the center of that cylinder is your axis line. Usually that's your datum line, which is your datum feature line. Yeah, and then the center plane, of course, for non-cylindrical feature is also established as your secondary datum. Remember the reference plane that we play with? Yeah, two of the examples are part 1. So your RFS, the parallel planes, yeah, is going to establish the zone for the center plane. So here it's like we're just talking so complicatedly, but you're just dealing with finding the axis and trying to find the center of that by using the plane. Yeah, if I have to put it in a very simple way, that's what you're doing. And then of course you use a tool like a gauge to establish that axis. Yeah, and since we are talking about it, sometimes your brain is cluttered with all that new information, so you can't be able to see it very easily. But it's very simple. It's trying to find the axis, and we call that the datum feature. In order to find the axis, you have to use a simulated datum, which is actually a tool. Yeah, and we try to use the different planes to locate the center. Yeah, so that's what we do in each of the example. Of course, we throw secondary and tertiary datum as needed, depends on the part, yeah, and the function. Okay, so let's go into the very first one. Because the original presentation is so bad because of the blue color thing that the author used. It's just so hard to print. We try to make as easy as possible for you, so it won't take the entire ink from the printer. So whatever, yeah, we recommend that you read digitally, so that way you don't have to print. If you do want to print, yes, I try best, right? It takes me the entire day, about 10 hours, to clear that blue thing out. Oh my god! And he was doing all the macros on it. You have no idea how hard it is to break that thing. So anyway, so this is because we have to provide the student a printable version, yeah? So that's a job of the professor, trying to deal with all the bad authors on slides. I think I gave him a review like that. I think he's cussing me right now, whatever. I throw in a review, oh, please give us something usable. Presentation slide for the professors and the students. Oh my gosh. So anyway, so we go in this, of course, this is the same example. Yeah. So we're still studying how to select and orient the datum feature, which is your here, here, here. Yeah, these are little triangles that you can spot all of your datum features and your primary, secondary, tertiary, and this is your single, which is your datum feature. Datum feature, 2 of them, so primary and secondary here. And don't forget to customize yourself with the different views so you can be able to understand where these surfaces are on the actual. I totally recommend you to throw and draw that on your application of your choice, AutoCAD or SolidWorks, easier, yeah? And try to get the isometric view so you can be able to see these surfaces, yeah? Please do. Of course, you do your 2 feature control frames, yeah, to throw your secondary datum and also your tertiary ones. And again, the controlling perpendicularity, so we're dealing with the 90-degree this time, because of this, see this little symbol right there, yeah? So your D is gonna control this perpendicularity in your part, yeah? So in order for you to find the perpendicularity cannot happen if you don't have two surfaces, yeah? And of course that is controlled by the datum D, which is this guy. So there's got to be this surface and that surface, yeah? Or you can also go with this and that, by the way. So anyways, it depends on how this example is going to do it. And then of course you have your datum axis E, which is right here, yeah? Here, this there's a little partial hole right there, okay? Okay, so let's go into the next page. So here your feature control frame, okay? So we're talking about the position of that two little thing right there, yeah, diameter. Your tolerance given to you with the max. When I say max, that's your maximum material condition, your little m right there. And they of course are positioned relative to your datum plane, which is your D right here, yeah. And then of course you have a secondary as E, and tertiary is going to be your F. And that datum E, yeah, and that's your RFS, which is your feature of size. R mean just regardless, you know, feature of size is right there. That's going to be controlling this, okay? And it's going to be on the axis, of course, because that's the see like how it's showing this hole right there, which is symmetric to that. And that's a datum E is a secondary datum, and that's a regardless of feature size, because it doesn't matter how it rotates, yeah, it's not going to disturb this control frame at all, because it's symmetric from here to here. And that's your center of rotation, so it's right here. So that's why we use the regardless of, yeah, feature size. And then the tolerance zone got to be oriented perpendicular to that datum plane right here. Yeah? Now don't forget you're dealing with a section view, yeah, and you're dealing with the exaggerated, all right, diagram. See this imperfections on the surface like that, meaning like you're dealing with the section, and here you're dealing with looking at the interior, so it's you see that, yeah, right there. And of course, don't forget the perpendicular these two planes are, which is right here and right on the cut surface. You can see it on this view. Yeah, you should master the view by now. Anyway, so we have three datums. Yeah, clearly identify in this diagram right there. And of course, your datum D, okay, which is your primary datum right here, yeah, and that plane is right here, yeah, datum plane, and completely, exaggerated view, exaggerated, okay, surface you can see. So where your simulated datum is going to be there to establish the datum plane D. So it is simulated by using the surface plate or machine table. So these are the tools to establish that datum, okay? Of course, that's your true geometric counterpart of your datum feature. D is these things, yeah? Surface plate or machine table, physical thing to establish that datum plane over imaginary, yeah? Plane D. So you can locate all the features from it or measure. And we're going to be considering a situation here, and where your regardless of feature size is your control, yeah, and you're going to use it with the here, yeah, a larger circumscribed cylinder, and that's going to be in contact the same thing with the high points of your feature, and when we try to establish that, yeah, datum axis, of course. And the feature axis got to be perpendicular, yeah, to the datum plane D, which is, of course, datum axis E is here. Yeah, your datum plane, center plane, okay, for this is F, and this one, okay, is your datum plane E. So I have altogether primary, secondary, and a tertiary, yeah? So each location. And we will be using all of the three datums to measure all of the features on that part. So when you look at it here, so that's your datum center plane F, and that's your datum axis E, and that's the control frame showing you, yeah, here, okay, and that for E is for the center right there. So that is going to be the feature got to be verified for that size, yeah. And you can use the parallel planes. And that's got to be with the maximum separation, yeah, don't forget it. External smallest and internal largest. Then, of course, you're using a gauge, yeah, to establish the datum center plane, which is your F right there. Yeah. This is the center of that feature right here. And it's got to be perpendicular to the datum plane D right here, yeah, because it is related anyway. It's just the view is different, and also perpendicular, yeah, to each other. Also, it's got to be aligned with this, yeah, datum axis E, because they're sharing. Look at that, yeah, that plane anyway. And your datum plane D, I already show you here in the first slide. All right, then we will get into secondary and tertiary datum feature. So that's your maximum material condition. So your datum feature size is going to have a MMC, yeah, fixed or non-variable gauges. It's going to be used to establish that datum. Now I have told you many times, yeah. Now you got the idea just by listening to, hey, I need to have a tool or a gauge or an equipment to establish or to find, yeah, that datum, primary or secondary and tertiary on the part, okay. So listening to the lecture is very important because you get the repetition of these new terms, okay. So if you listen 3 times, you totally get it. So your gauge sizes, again, it's got to be determined by your material, your maximum material condition. And of course, you will also look at the geometric tolerances. Why? Because it's very important, yeah, when you join the parts together. Okay, then we'll get into another example, which is this, yeah, same block that we use in the beginning. And here we will look at this, yeah, material, maximum material condition. Because your control, of course, see, usually you see this with the datum theta. Right now, yeah, here, and that's gonna be here with the datum E right there, okay, which is the axis of that, yeah. So, and here also your datum F, yeah, and that's gonna also have your MMC. Okay, so E has an MMC, then F has an MMC. Okay, because the set is so here. So when you put it here instead of this control frame, I stick it into here, you know that there's a maximum, yeah, material condition with that tolerance right there, which is here written there for you. Okay, and that's a 0.2 for this. And that little diameter is right here, 0.2. Yeah, you have primary, secondary, and of course interrelated tertiary right there. Okay, because there are different features right there. This feature and that and this. Okay, and of course from here to here about 60-degree, yeah, angle. And that's for the D, yeah, which is your primary data. It's going to control that, which is also, yeah, related to your secondary, yeah. So we can be able to see that very clearly for remember each one of them. Just go slow to read it, but you will get it. Then datum D, yeah, and that's verified for the surface accuracy. You need about minimum 3 points because it's a primary data. Yeah. With that point, it's got to be in contact with your datum simulator, which is usually a tool or equipment. And then your cylindrical, yeah, gauge. And we still have axis E, yeah, have a max MMC, which is there, and that's got to be perpendicular to your datum plane D. We're seeing the same, yeah, part, so you should be able to get it by now. And then your cylindrical gauge, yeah, it's going to establish the datum axis E, and that's going to be perpendicular to, again, your datum plane D. Okay. So when you think about the fixed gauge, yeah, that's which is equal to this one is for the F, also as MMC, yeah, and it's going to position perpendicular to your datum plane D, and also your center plane is, yeah, aligned with this E. We have already seen that in the previous diagram. So secondary and tertiary datum features, and we're going to go into least material condition. So we'll have to establish the primary datum, yeah, and so that datum can be axis or plane. But now instead of the MMC, we're going to head to the LMC boundary. Okay, so let's take a look at it. So we do have to find the secondary and tertiary datum. And they can be also axis or center plane, yeah, depends on the true geometric counterpart of that features. So here we go back to the same part here, yeah, but now the control, yeah, is going to be modified because we're now dealing with the least material condition. Okay, your D and E, your F, okay, which is here, DEF, the same thing, yeah. Your D on the plane, and then your E here, and your F right there, okay? All right. Least material condition. Datum axis doesn't really change. Your datum D is also verified in the same way. And you have 3 points, the same thing, yeah, with your primary on datum simulator. And we have our dashed lines right there, yeah, that's the only difference that you have from this MMC. See how different that is. Here for MMC, we use a solid line. And we go down, okay, how it is not inside. I'm going to go back again. It's outside, see? And this is the wiggly thing is your rough, exaggerated, diagram for this whole, because it's showing the imperfections of it. Your MMC, your hole is outside of that. Your LMC, your hidden part is, see? Look at that line is inside, yeah? Your surface, the actual surface is outside of that. So that's the only difference that you have to understand, yeah, when you deal with the LMC stuff. Of course, you can also see here, yeah, because you also have for the F, yeah, you still have LMC. Your E has LMC, your F has LMC, and then of course your D, yeah, is connected to that. So therefore you can see if you look very carefully the dashed lines, yeah, representing your LMC surface right there. So that's done with that, and if I ask you, you should be able to draw it, the difference between MMC and LMC in the diagram. And then of course in the datum precedence material conditions, so let's see our order. So your order is again read from left to right, yeah, in your control frame you can see these datums, and the precedence is going to go in order, yeah. Your simulated datum is going to get in contact with them, so 3 point, 2 point, and then 1 point. Don't forget that, yeah. Your material condition, where your datum feature applies, got to also be clear, yeah. then your order precedence, yeah, is very important because it's going to influence how your part, okay, will inspect example or function. So let's take a look at an example. So when you look at this example, we can see the orientation and inspection characteristics, okay? And we will take a look at our significance and interaction, yeah, between the datums and also your material condition specifications. So that's our first example. Control frame goes straight in, dealing with the MMC. So therefore your solid line got to be outside, yeah? And then of the material of the real surface. And then here is your tolerance. Here is how many of, that tolerance is referencing right here in this reference control frame. You have two datum, which is A and B, yeah? So these are their surfaces. They are 90 degrees to each other, yeah? So this datum A is going to control that, and this is going to control, yeah, this. All right, and then we'll get into an exaggerated diagram right here. You can see the datum A, regardless of feature size, and we have another datum which is B, which is right here, yeah. And of course, you're still dealing with the maximum material condition, okay. So your datum A, okay, is right here. That's your axis. Yeah, and that's your primary data because it said so here in the control frame. And it is to be controlled regardless of your feature size. Of course, when you establish the datum, we're going to use a gauge, yeah, and the gauge is, since you're dealing with the axis, your gauge got to be something that can be able to establish that center line, yeah, which is your center axis. So the gauge axis and the datum axis relatively got to be at the same location or position. Of course, when you look at it in the two dimensional, it's a little bit difficult for you to be able to see the gauge around it, okay? And your gauge plane is right here, the red line, and that got to be also perpendicular to your datum axis, which is this guy, yeah, 90 degrees to each other. So the smallest circumscribed cylinder is going to give you, yeah, the external, yeah, diameter of it. So that's you can use a variable gauge in contact with the high points of your datum feature, which is your A right here, yeah, for that. Okay, and here is your control frame. We're just reiterating the same thing where you can get the cylindricity because of this symbol right there. Make sure you study all your symbols so you know which one is what, yeah. Portion, cylindrical portion of that part, and it's going to be controlled by the primary datum and then secondary datum right there, yeah, regardless of your feature size. And of course, that's your RFS. Datum A is a RFS. Why? Because it is a feature of size, okay? Feature of size means that's in the word, yeah, the feature. Of course, you're dealing with the size of it because it is a cylindrical portion of that part. Then we're going to use a variable gauge, yeah, to verify the accuracy of these datums. Then that gauge is going to compress around the diameter that you are trying to establish the axis in, and of course your high point is always there on the surface, and that got to be in contact with that gauge, yeah, otherwise you can't be able to establish properly for the axis in the cylinder. And the separation, of course, it depends on the perpendicularity, you know, of that two, your axis and the gauge plane, yeah, which we show you right here, yeah. Okay, and then your RFS, yeah. So in our example, your cylindrical tolerance is 0.2 because it said it so right here. It's also, yeah, I also stick it into here so you don't forget it. And of course we are in metric, that's why you have 0 right in front of that decimal. So when you look at it, don't think like, am I in inches or am I in metric? It is in metric, yeah, you know that. If that's in inches, we won't write the zeros, yeah. American don't write the 0 in front of the decimal. So I have already told you about that several times, yeah. So which the axis of the cylindrical portion of the part, yeah, got to lie in that tolerance. And you know that, yeah? Anyway, so the specification controls the perpendicularity of that cylinder portion relative to that datum plane, okay, B. So now let's go into here to take a look at the datum plane B, which is going to be right here, yeah? Right now, in this case, we're going to bump it up, do it as a primary instead of like that in the previous example. So this control frame is changed because we're looking at the datum B as a primary, which is this guy, okay? And then datum A as a secondary, which is this guy right here, yeah? And the red one is your gauge plane, and the gauge axis is right here along with your datum axis A, because we're using a gauge to establish the axis of A, so the gauge axis is about the same as your data axis A, okay? Datum axis A. Of course, then when you're establishing that, you know that you have about 3 high points for that B in contact with the gauge, okay? So those gotta come very, automatically in your head, all right? Anyway, so your smallest circumscribed cylinder. So there are two things going on. One is an inscribed, the other one is a circumscribed. Okay, inscribed it inside, circumscribed it outside. So make sure you try to pay attention to these differences. Now don't go so fast like I do when you're studying for the first time. Go slow, okay? Alright, then get into the explanation of this control frame. So we're still dealing with the datum feature B as a primary datum, and then your cylindrical extension on the part is a secondary datum, which is your A, yeah? Because we flip it, yeah? So the cylindrical part is now the secondary. So then notice once again that your datum feature A is held with your RFS, okay? Regardless of the feature size, there's no issue. So verification purposes or what we do, yeah? In this circumstance, we're going to require the flat portion of the inner side of the part datum feature B. This is just doing a verification of your dimension stuff, yeah? So minimum 3 point got to be in contact, yeah, with your tool, which is your gauge in this example that we're using. And you maintain that contact, and then we try to play with a variable cylindrical gauge because you're establishing that axis in the plane. So in this case, your primary is datum, so you will stress on the datum plane B with 3 points, yeah? And these points are your high points on the surface of that datum, yeah, feature. Okay, so the smallest inscribing cylinder, yes, again inscribed, which isn't circumscribed, okay, they're different, and establish that main part envelope, okay. Then we'll get into material, yeah. So here in this case, we have a maximum material at A and also maximum material, yeah, to the 0.2, yeah, which is this little, yeah, hole right there. Okay. And so the surface B, where is going to be right here, datum plane B, and that's your primary datum feature in this case, yeah. The datum feature A is going to be your secondary with the maximum, yeah, material condition. So since it is a maximum material condition, you understand that, yeah, it's got to be outside of that surface that you're looking at, yeah. And then the fixed cylinder gauge, you have a diameter that is equal to your virtual condition of that, yeah, datum feature A, and which is going to be perpendicular to the datum feature B, okay. So that's what we use to verify the part in the simulate example. So I believe at this point you should be able to get it. Yeah, the only thing that comes for new is right here. The secondary has the MMC. So meaning like this thing that you're drawing, yeah, got to be inside, yeah, got to be inside, yeah, of your MMC is got to be bigger than your actual part. That's all you need to know. Okay. All right. So here your diameter A, okay, which is this one. Why is the diameter? Because you're dealing with a cylinder. Cylinder right there. Yeah, cylinder has a diameter. So that's what the control frame is about. And it is with the RFS, yeah, regardless of feature size. And you are going to go away from that perpendicularity, yeah, between your datum axis and your datum plane right here. Then when it comes to here, now see that how this is perfect and this is like kind of like a deviated away. So your surface B is your primary datum feature. Yeah, see, it's change. And then datum feature A is your secondary with RFS, regardless of your feature size, you're okay. So the mating envelope, okay, is your smallest inscribing cylinder. That is going to meaning like, since we have a maximum, so the real surface is inside of the max, yeah, so therefore you have a smallest inscribed cylinder that's going to be in contact with your high points of your diameter A and is perpendicular, yeah, to primary datum feature B. So if you forget about it, I can draw that out for you. So it's like wiggly things like this in your maximum material, okay? It's like this, and we call that inscribed, okay? Yeah. So you can draw like I do, so that way, yes, you can be able to see it, okay? Don't forget that, of course. All right, then we'll go into the next one, and then we put the max, yeah, right here. So your surface B right there is your primary datum feature. It doesn't change from the second one. And then your datum feature A is your secondary, and we are going to apply the maximum material condition to that. So you have a fixed cylinder gauge, which is right here, establishing this axis right there, yeah, and also, of course, this plane. So that's the diameter of that cylinder, yeah, and also is perpendicular to this datum feature B plane right there, okay? And we will definitely use that to verify the part and also simulate the assembly. Okay, so now you get it. So multiple datum features is going to be used to establish a single datum, and we call that the co-datums. Yeah, so you have a single datum, multiple datum, and we call the co-main lines happening at the same time. Yeah. So in some of the condition, sometimes it's okay to you have to to establish a single datum, and you're going to use more than one datum feature on a part. So meaning like you're using a single datum, but you're using it on more than one feature, yeah, instead of one datum for one feature like we have done so far. So in this case, one datum for one or more features, yeah, on that part. So in that case, you have your both datum reference letters and also associated Zeiss feature datum multipliers, yeah, which is your MMC or LMC, if applicable, and you enter that the datum reference cell in that feature control frame. So let's take a look at it. So if you have like a two datum features and separated by a dash, yeah, I will show you as we go into the example like this, okay? So you have two of them right now, and C and then dash D. So that's what it is saying, okay, right here. So two datum features separated by a dash. So they're specifying to establish a single datum, yeah? Even though we're using a two, we're just reading it as a single datum because kind of like a tie to each other, yeah? So that's what it's saying here, and one is not considered more important the other because they are equally important, so we put it in a one cell, yeah, together. It's kind of like a married couple living in the same house like that. They both are equally important to each other. If not, you get argument. Yes, meaning like we'll have issue. And so in this case, you can put two datum in the same box if you don't have the same, yeah, the same significance in the feature on that part. So make sure when you choose, you're going to choose very carefully of the same importance or significance. Okay, so that's the trick of it. So now, so both features have equal significance. Your datum reference letters got to be entered in any order, yeah? And we will use it within the cell of the feature control frame, meaning like put them in a one cell box, yeah? Don't separate them into box because they're equally important to each other, yeah? Important to each, no, I shouldn't say important to each, they're equal to each other, important to the part, yeah? Okay, so sometimes you have like a more than one surface, and that's more than one surface is significant, yeah? So we can tie them in, that's what it's saying about. So here in this example, you can see the two surfaces, yeah? The two surfaces, when you look at it, they're all symmetrical, this part and that part, so they're the same. So therefore we box them all together, C and D, yeah, datums. And we call that, of course, co-datums.
I didn't catch that.
So datum features C and D can be combined into a single, yeah, reference, which is right here. So symmetric features are very easy to identify for their equal importance. Okay, so the order again of their placement is irrelevant because they're symmetric anyway, the same, yeah? Okay, since they're the same, you don't have order. Then the combination of the both surfaces, the combined characteristics become your datum feature, and in symbol we're going to write C-D, yeah? And make sure you remember the order has no bearing on the significance because they're equally important. Alright, now we're going to exaggerate, yeah, so we can see the rough surface right there. And of course, so you have to determine that datum C and D. We're going to position the elements on both surfaces so you can evaluate at the same time, yeah? So we'll consider how to establish the axis. Yes, we're going to use a multiple datum feature. So here you have a parallelism right there, yeah? Since you're dealing with the parallelism, you have to have two surfaces, yeah? That gotta go with this, the tolerance control right there. So your datum plane is right here. Since we're exaggerating, it looks like it's not perfectly horizontal. Alright, single datum axis from two datum features. So you have a single datum axis, but you have a existing or coaxial diameter. So at that time, you can be able to establish a single axis. But you have a coaxial features that is using the same axis, just like the one that we just deal with in the previous example. But now our datum is not plane; it's going to be axis, yeah. So they are simultaneously contacting the high points on both surfaces. So let's take a look at the example of that, and you can see right here your datum axis of that first example part, okay, is going to be established by the two datum features, which is you have two diameters here, yeah? So I'm going to put A and then B and then C, all right here in this control frame, and you can see that A and the B, okay, sharing, yeah, the first circle and then the second circle and the third circle. So you have first, second, and third, first, second, and then the third, okay? So A and B, they have a maximum material condition. C doesn't have it, so we can be able to combine this A and B all together because you're sharing the same axis. All of the three datums are sharing the same axis, but you cannot put C with A or B because of the material condition. And you have A and B the same material condition, so you can box them together, yeah? So then we will exaggerate and take a look at the diameter of that cylinder, yeah, right here, and the axis is right there, and diameter is right here, yeah, of this bigger cylinder. Of course, since you're dealing with a max, your actual thing is inside of your max, okay? So now you can see your datum axis is a primary datum reference, which is A, and then B here, yeah? And then, of course, a C is go down to the next cell as a secondary. of course, this is your primary. The whole thing is because you have only two right now. Yeah, if you don't forget, your datum order is depends on the significance. Yeah, of your function design. So right now, since you have a max, yeah, for A and B datums, and you can combine that, and they both become primary. So therefore, the precedence is going to be on the left. Yeah, and C doesn't have a max, so therefore it go down. And of course, this is controlling this, which is your smallest, yeah, small hole. All right, the next example, we have this right part, which looks like this in your ISO, yeah, in your pictorial, yeah, looks like this. Of course, in 2 dimension, we draw like that. Okay, so I feel like there's something missing, but I have no idea. Yeah, something, I think this should be a tolerance or something. So anyway, so right now we're concentrating on the two datum features, so you know that they are equally important, yeah, and therefore there's a primary datum, which is this, and then your A is actually from here to here, and your B is right here, but then they are equally important, sharing that axis right there, yeah. So thus this little, right, a symbol is your circular Raynaud. Yeah, so when we come to the Raynaud tolerance, you will learn about this. At least you should get the symbol of that. Yeah, if you don't know, I'm telling you that now. All right. Then yes. So okay, I'm so tired. Alright, so anyway, so datum feature A is right here. Yeah, this is just exaggerated drawing showing you the imperfection where your surfaces cannot be so perfect, and there could be a little bit of deviation from your tolerance zone. Yeah, that's all that these things are. Of course, in real life, it's not like that. Yeah, if you get like this in real life, oh my gosh, that'll be a trouble. So anyway, so you can see right here, and your datum AB, which is equally important to each other, which is your primary datum. Yeah, in this case, your axis is right here, is showing you right there very clearly. Your B and then your A is going to be right there for their corresponding feature. Yeah. And they are, of course, coaxial circumscribed cylinders because you're dealing with the axis. Yeah. Of course, you have the same centering because they're sharing the same axis. So the gauge axis, if you try to establish the axis by using gauge tool, yeah, and the date to show that the datum axis, yeah, datum axis is there. Where is the datum axis? Physically, it is a center, and it is the axis of the gauge, yeah, which is the tool that you use to deal with that. So you know approximately, oh, the datum axis is right there, and start imagining it, yeah? Okay, so partial surfaces datum feature. So let's take a look at it. So it isn't always convenient to use the entire surface as a datum feature, yeah? So sometimes you have a situation where you can use a partial features, yeah? So it's easier to handle than the whole, the whole surface. Why? Because you can understand the procedure, to specify only a small portion of the surface. Meaning it's easier to handle in your drawing. Okay, so we are going to do. So in order to do that, first what we do is we're gonna do the chain line draw, and that line gotta be parallel to the surface profile. And then you're gonna dimension for the length and location. Yeah, you always need the value for these things. Then you need a note, and that note is gonna talk about the special limits, your physical limits and orientation, of that area. And then the last one is you need to put the datum targets. Yeah. Okay, so and that method is pretty acceptable, from the practices, and of course they're going to represent the appropriate alternative, instead of always using the entire plane, entire surface plane. Okay, Okay, so let's take a look at the partial surface method. So here is our part, and of course you can see the larger surface, the small area, yeah. So we're going to use a small area to identify the datum feature, yeah. So first you're going to use a chain line like that, yeah, see that? And it is a little bit offset from the edge view. Offset means, see, like how it is lift up and then your datum feature is stick on it instead of the entire plane, yeah. So that's what we call the partial, and that is where the extent of the area where this datum, yeah, is going to be, and that chain line again associated, yeah, with your basic dimension, which is this guy, and we label that, yeah, in it. So here we go, and here and here. Of course, these are just a measurement, yeah, that we use from here to there, and then of course from there to there. And I'm going to use a gauge and try to establish that, yeah, plane. So that's what we're doing right here, gauge, try to establish this plane right there, and we're exaggerated, yeah, in a diagram right there. So you will use that datum simulator, which is your gauge, to verify, yeah, this place, this plane. So use that to locate and verify the related size and your location of the features. All right, this is your work, and you have your assignment in every, yeah, chapter. So you're gonna go in your book 58 to 60. If you cannot buy the physical book, you can do the virtual, which is digital book right there, about I think $20 down, I believe. I'm not quite sure. I believe around that range. And go to stcpublications, yeah, .com, and you can get it from there. Those, I think everybody got one, except a couple of students. Okay. I would love to share my book with you, but the issue is like that's in the instructor account. So, I just do ebook most of the time because I hate carrying the book all around. And the one that as the department you can rip it out, so that's also is pretty difficult to like take pictures and things like that. So make sure you save your money. Yeah, don't eat at restaurants or anything like that, or don't buy clothes and things like that. Save your money to get a textbook. In technology, you definitely need a computer and a cell phone. So save your money to get these things. Make sure you prioritize what you need at this phase of your life, yeah. And reduce all other stuff to make money. If you have money, then go ahead. Yeah. If you don't have money, make sure you have to prioritize your money to use in the right way. Okay. So don't spend, you don't need to buy 70 something dollars of game. You don't need it, okay? So reduce all of that and you'll be okay, okay? I don't want to say these things, that's not my business, but I am gonna say it anyway, yeah? So if you can be able to use it, use my advice. If you don't want to use it, don't use it, yeah? It's up to you. Okay, so you do the problem 58 to 60 in your textbook. If you don't have it, come to me and I will go ahead and copy or do something for you. Yeah. Then you're gonna find a series of the question problem statements, and you will try that. And I will also show you, of course, in the slide, so you kind of get the answer. Yeah. You should also get the same slides. Yeah, from your textbook. Okay, so textbook is important. Your assignment shouldn't be taking any of time. Those of you who don't know what they're doing take a long time to do the assignment. Those of you who know, because the answers are just right there. It's not even tricking you or any of that. So you should be able to do the assignment very quickly. And I don't understand why some of the students cannot be able to bring assignments up, just pure lazy, or I don't know what's going on. So again, the answers are right in the slides. Okay, the answers is just right there. You can have access through your book, okay, by downloading it. Also, you can get access to the answer by listening to the lecture. If you don't do both of them, I don't know, okay? That's why it's taking a long time to do an assignment. And you've got to practice to be on time because everybody come to school, about 80% want to get a job, but getting a job, you have to train yourself to be on time, okay? You must do that. And you're practicing with different courses by turning the assignment in. Doing the assignment is doing the work, okay? Getting the assignment in is being on time. And these skills are very essential. So when you are a student, you have to practice, all right, these things to enhance these skills. So if your boss want you to be at 7 o'clock, of course you get at 5 o'clock and get there at 7. If your boss want you to be, there at work at 10, then you have to start to do from 8 o'clock. Okay, so also depends on the driving distance. Calculate all of that. So you cannot change yourself when you go to work if you don't start from now. So I am targeting the younger students, so you can practice and then enhance these skills to be on time, to complete the work. You have to practice. So university and high schools are different, okay? University is kind of like giving you this strenuous training in a very limited time, and if you can do that, you can do the work. If you cannot do that, you cannot be able to do the work, period, okay? Because you are having the habit of avoiding, procrastinating, doing all at last minute. Don't do that. You need a careful plan. You need goals. You need objectives. What you are going to complete. Every hour, every day. Every week, every month, every year, every 5 year, 10 years. So that plan got to be drawn. Whether they will come true or not, you need to have that. Okay. So do that, please. Okay, so let's take a look at the exercise. And I do that for you. So this is your job. Okay, I'm not going to read all of that. Please do all of this. And problem numbers are given to you: 58, 59, 60. Datum targets. I'm going to get into it. Okay, so datum targets are like surface types. So you have like a bow surface or non-planar or uneven surfaces. That's come from your machining, like casting, forging. And then you have thin section surfaces come from warping, another machining process or manufacturing process. And they got to be effectively matched with your datum reference frame, okay? So anyways, now just reading, we will get into exercise and what they are. Right now, just to try to get in touch with the terms. So datum features must contact datum simulator. Again, your datum simulator are some sort of tools to establish where the datums are, and also you have surface curvature, irregularities, and then your roughness. Some of the surfaces they're not very appropriate to use as datum feature. So we're going to take a look at what they are in this datum targets lecture. Okay, so in this case, what we're going to do is we will use the datum targets instead of datum features, to combine to establish the datum reference frame. So let's see, datum targets, they designate the specific points, lines, areas, So what of your contact on a part, and we're going to use it in establishing a datum reference frame, okay? So here, datum target, symbol, line, target areas, and then also like this, okay? So there are 3 different datum targets: your points, your lines, your areas. we already talked about it in dimensioning and tolerancing. Yeah, they're drawn with your bold lines, and then of course the symbols for a datum target point is in the form of your large X right there. Okay, that's just a point. Your datum target line is a bold line, yeah, and then it looks like a phantom line because you have two dashes, yeah, in that datum target line. Don't forget the two dashes. And then where's and then of course your datum target areas, yeah, looks like the section lines, yeah, so phantom lines with the crosshatch interiors. So the phantom lines in datum target areas is right here. See, look very carefully, the borders, you know, the boundaries. Look at that. And then of course in your like the section lines, 45-degree lines, yeah, right in there. Okay, so I might ask you to draw these things, yes, in the quizzes. All right, and so we use these symbols, and we're going to establish the datum targets and put them in our drawings, engineering drawings, yeah. And then they are sometimes used in conjunction with your target points, line areas all together. On the part, yeah, you use a radial or straight leader line to show them in your drawing. So for targets on the visible surface, you have a solid leader, yeah. Targets on hidden surfaces, your leader lines are dashed, of course. Your leader lines typically do not have a horizontal shoulder where they originate at the datum target symbol, and they never end with an arrowhead. Your datum feature symbol is going to be attached, yeah, to the appropriate views of surfaces and that have been designated as datums by the use. Okay, he made a lot of grammatical some mistake. So anyways, the datum by your datum targets. Okay, all right. So let's take a look at the how to use them. So here we are. Yeah, there's a point, there's an area, and there's a line right there. So the symbols are used to identify the datum target, location, orientation, size, order, precedence, yeah, in your drawing, of course. And then we also relate, yeah, each one of them to the datum reference frame. Look, yes. And we use a solid and a dash leader line, which is this, and that. This is a solid, that's a dash, that's a solid, okay? Leader lines. So sometimes make sure that you notice the optional use, yeah, for the horizontal shoulders, and also the absence of the arrows. See, no arrows right there on the leader lines. So just straight line, dashed or solid, okay? And use a bubble, of course, to show them. Okay, so point. So let's take a look at the datum target point. You're going to indicate with a symbol like this, okay? Of course, a normal view, your basic dimensions. Sometimes we use like this to locate that datum point. Okay, so here's the basic dimensions, and now here you can see the datum point right there. Yeah, the datum target point right there, showing you. So the basic dimensions are your gauge dimensions or your 2-maker tolerances. Yeah. So it's easy for you to locate when you're doing the manufacturing or inspection in real life. So there are no tolerances for datum target location dimensions on your drawing, and they're not tolerance again in feature control frame. Okay, no. All right, then let's get into this. So you can see the single point contact at the base location right there, and you have a spherical tip gauge pin is attached to this part. Yeah. So this view is going to interpret the last slide. And you can see that show the point contact right there on the datum feature during your manufacturing or inspection cycle. Yeah, so this is your single point contact at basic location with a pin. Now line. So datum target line, you can use it, of course, and the symbol is your phantom line, yeah, on the normal view. The target point symbol, sometimes we use edge view on the surface, yeah, sometimes or both. So let's take a look at the example. So this is your point, and your line is going to be right here, yeah. It seems like it's kind of weird. Okay, I fixed it. It take me like about 10 hours, yeah, per slides, per presentation that this author make. The slides are so useless, like really. It's just giving me headache the entire semester doing this. Like, I couldn't believe it. I mean, I believe that the author, like, they should use a white background, considering for the students on school. We don't have that much of ink to print, by the way. So anyway, and it takes a long time to fix it. Oh my gosh. So anyway, so let's go back here so you can see, this is showing you that's a point and that's a line right there, and that's your phantom line right here, yeah. So you can see the datum feature symbol on the edge view of your datum feature, and then your target is also located with the basic dimension, which is this one. I can see it here either. So let's just imagine there is some dimension right here, yeah, from here to here. I don't know what the is. Maybe you can go back to the original, presentation. You can be able to see some links there. They were trying to get rid of the bleach, the blue background of that slide, and sometimes you get rid of some stuff right here. So anyway, so pay attention. I don't need it. Yeah, for now you have some dimension right here, from here to here, and here is your point, and here is your line. If you could get that, that would be great. Of course, they are actually, you can follow the dimension to locate the targets, yeah. So target or datum targets. Okay, and then the next example, you have your gauge pin is going to be stick right here to be able to find the targets. So this image is going to show you, the datum target line application where that is going to be, by using this gauge. So we now know that this datum target is right here, yeah. So the gauge pin is going to make contact, with your exaggerated, of course, your single line element of that datum feature surface, yeah. So you can be able to locate this by using this physical gauge, yes. Okay, now area. So let's go into area. So there are many times that when your single point contact, okay, you gotta determine that, and sometimes it can be insufficient. So sometimes we're going to use the area of contact if that's necessary, yeah. So we use the datum target area for some of the situations, yeah, in your drawing. So the datum target area, we're going to use a bold phantom line, outline, okay, the boundary line, of course, and with the section lines inside, yeah. So let's see, basic dimensions also used to locate that area. So here, yeah, that's what we are seeing right here. And here, of course, this is a basic dimension, and you can be able to quickly spot, yeah, the area target, which is this guy, okay? It's supposed to be phantom line, so this boundary are kind of weird, the way that I believe that, I don't know what he's doing right here, let me see. Okay, I'll fix it. Okay, it's supposed to be like this. So there's so many things I need to fix this stuff. So that's your phantom line, and then your section line. So we know that you can quickly spot by using this basic dimension for this datum target area. Okay. All right. Oh my gosh, I have to fix this thing too. Okay, I'll fix it. So anyway, so this is your datum target area. Yeah, you can spot it from this basic dimension, and then the diameter of the circular target area, because this is circular, yeah. So and this is your target area, and you can see in this, yes, symbol right there. So it's showing you the diameter and then area. Okay, you can either give this or you can either give like this. Anyway, you can go back to the original and to see this. I believe that yes, it's supposed to be like this. Okay, I did fix it. It's taking a long time to do fixing all of the slides, the very best slides Alright, now we'll go into the location and size, your datum targets, yeah. And of course, you will go from your basic or tolerance dimension, meaning like if you spot, yeah, the tolerance dimension, you can be able to reach to the datum targets place. That's what's talking about, and you can in normal cases, okay, you will use your gauge and the tool tolerances also to identify these datum targets. Yeah. Of course, your gauge makers tolerance is about the same as your datum targets tolerance. Of course, most of the company have their own standard, yeah, and you follow what they're doing. Don't go and do what's the common standards are. Sometimes they follow the standards and sometimes they don't. Sometimes they know and sometimes they don't know, okay? And you know more than them. And then, of course, you have to deal with these people. All right, so combining target symbols. We'll get into it. Okay, so in this example, we can see our datum is right here, your primary, yeah. It's going to be right there, and this is our part views, and you can see the point, yeah, datum target point, datum target here, line, okay. I don't really see the area for now. So we have two of them in here, yeah. But that's the two views, the same part. And then of course we have a one line right there, okay. Of course, and here are your basic dimensions right there, which when you spot it, you can be able to trace all the way to the datum target points right there. Okay, so make sure you study this until you get the where they are, so you can quickly locate them. Okay, and here also basic dimensions. So if you go along that, you're gonna find, see, your datum target line. Okay, then we're gonna put a gauge right there in order for us to establish that datum targets. So that is going to be in contact with that, so you can be able to spot the target line, datum target line, and here you can be able to spot the datum target points. Yeah, so that's where the spherical tip gauge pins points are going to be in contact. Okay, all right. So that's just showing you how you spot them or establish the primary datum by using gauges, which is your simulated datum. Okay, so here is you have a CAD, which is your computer aided design, which is your computer generated image, which is going to help you understand the placement and orientation of the gauge pins, which is right here and right there. So you have altogether three of them in there, to establish the primary datum. Okay, then we'll get into datums derived from the offset surfaces. So your datum targets, we can use them to establish a datum on stepped or the offset surface, meaning like offset meaning like raise a little bit from the surface, yeah. So you're going to see the offset distance between the datum points, and that's got to be always be a basic dimension. So here we go, here, 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 and your basic dimensions are here. If you track it, you're going to get to it, yeah. And also right there, it's right here. Of course, right there it's okay. When you quickly spot, first in your diagram, you can see these things. So where's your offset? So when you look at it, the only thing that's been raised is right here, So that's your offset, and that's a 0.94. So we're in inches right there. So 0.94 plus or minus a 0.01. See? So the offset distance is going to be 0.94. And that's going to be dimension, basic and also tolerance dimension. So that's basic and that's your tolerance dimension. So your datum A is your primary datum, and established as your bottom. Yes, it is a bottom surface. Yeah, and but that's with the two datum points right here, and then the third datum target point on the offset surface. Okay, so you have 1, 2. And then this is your offset, all right, surface, which is your 3 is right there. So if you look at in two views, your third point is there and 2 points are right there on the same line. Yeah, we have 1 and 1 on the other side. Okay, so your basic location dimension is the distance between your datum target symbols. Okay, so you have these things, and then of course your non-basic dimension is the distance between the two surfaces. Yeah, two surfaces. Yeah, so that's your non-basic dimension. These are basic. Yeah, okay. Datum planes established by datum targets. So we're going to establish the datum plane by using the datum targets. So your primary datum plane, you need about 3 target points, and the targets you cannot be aligned in a straight line. Meaning like you can't use all the targets in a straight line to establish a primary datum. Your secondary datum, 2 targets, tertiary, 1 target. Yeah, so now we're seeing the contact points as the targets. So the combination of your target points, lines, and areas, we can use them together. So here we go. We have a primary datum D. Okay, it's going to be established by 3. All right, datum target, which is this, and then that, because that's staying together. 2 of them is right here, and 1 of them is right there, and that's going to be not in a straight line. Okay, 2 of them is on a straight line, but the other one isn't. So it's kind of like it looks like a triangle. So of course you can even establish that a primary datum D in this case. And note that the top view, okay, of your targets identify according to how they will project into the view, which is D1, 2, and then D2, 1. Okay, so we're going D1 and then D2. So you can see the D1, yes, on the top, and then go down. This is your front view. Okay, that's your top view. Meaning like D1 is going to come on top, and then D2 down in your top view. That's what you see. Okay, and then of course since you're doing like, since D1 is there, you got to put the D1 right there and D2 down there. Okay, of course, so when you do it in your top view, we're like just writing like D1 and then D2 down there. Okay, so pay attention to these little things. Of course, your proper projection sequences is always necessary, and you use them in projecting the datum targets between the views. Okay, so I believe that you mastered your view. I've been saying this like 3 or 4 times. Okay, then we'll get into the next one is your E. Yeah, so the primary datum, and then you have your secondary datum is right there. Yeah, established by the 2 datum targets E1 and 2. The same thing, and we are looking at your front view, and then that's your top view. The front view, so of course you're going that way, so you can see it from the top. So E2 is going to come to the front, yeah, and then of course the first and then the second is going to be E1. So you now know how to read in order of how we symbol them in the drawing. Okay, so in the front view, your E2 is going to be closer to your I than E1. Okay, then the order for numbering the projected targets into adjacent views, just follow which one comes first. Okay, and then place it in the views, and make sure you understand which one comes first when you put them into the appropriate view. Okay, so because you have a front and then your top. All right, then primary datum D and the secondary datum E, and then we're going to put the tertiary datum F, which is right here with a target point. So see a big X right there, and that's your single datum target point. Alright, then datum target planar application, so let's take a look at that. So here in this example, we have areas, of course your gauge pins, about 10 millimeter. I believe there should be a 10 millimeter right there that we can see. Let's show that. Okay, so I can see the basic dimension, so you can go back to the original slides and be able to see it, but don't worry about it. Just know that there is basic dimension for that. We don't need the numbers anyway. We're dealing with the gauge pins, and of course they have about 10 millimeter in this case, yeah, and their locations placements are right there on this part, and we're going to use a basic dimension to trace them, yeah. And of course you also have a two makers or tolerances, and your datum A is going to be right here to establish, okay. All right, now let's take a look at the gauge pins here, your surface plate, and then your part right there, exaggerated, okay, diagram right there, datum features right here, your plane, datum plane A is right there, and we're using this gauge to establish that, yeah. So you have a 1, 2, 3, and that's about like a 10 millimeter in size, okay. So these gauge pins are going to establish this datum plane A, okay. And that's pretty sufficient to establish other features and also feature relationships. So datum targets are used to establish a primary datum axis. So if you have like two sets of three, okay, equally spaced targets, then you can establish a datum axis when you're dealing with your single cylindrical primary datum feature. Yeah, so we bring our regardless of feature size again. Regardless of feature size, it doesn't really matter what the size of your feature is, yeah, it still work with this method. And also the two sets of your datum targets are spaced as far as a practicable and dimension from the secondary datum. I'll show you, okay? Don't worry about it. So now both sets of targets are using the same datum identifying letter. So here in this case, don't worry about these dimension, I can see it anyway. So anyway, so we have a B here, D here, yeah, and then our targets, yeah, showing you. We have different views. You know the order, B comes before B3, okay, and that's your friend, and then that's your site, okay. Then we have 5 and 6. Then we have B1 and then B4, and then your datum D is here and B is right there, okay. And your axes of course are right here that we will be sharing the datum axis B. So both sets equally spaced datum target points, yeah, here, 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 yeah. Then we use the same datum reference letter, which is this guy, yeah, axis B. So your datum target number again is going to increase to be 6. So which is here, yeah, okay. So your site view is looking this thing from that site, yeah. So therefore it's going to come this and then that. So therefore when you go to the site view, and this is your cut, all right, section view right there, you're going to see B5 and then B6, okay. So which one comes first? So B6 comes first and then followed by 5, yeah. And here your 5 comes first and then followed by 2, okay. So a little bit difficult to see it. Okay, that's from the side view, yeah. So make sure you practice that so you can be able to place them. Alright, so two different cylindrical datum features are going to be used to establish a single datum feature axis, which is your axis P, and then that each datum feature is going to be identified with a different datum feature symbol, yeah. So each set of datum targets contains different datum identifying letters, yeah. We already talked about that actually. We're just repeating again here. So again, your front view, your side view, yeah. Pay attention to the order, and we can be able to establish, yeah, this is your axis, and here is your datum C and B right there, okay. So now you have A and B at the same importance, yeah, because they're tied anyway. So that's what we call the single datum axis, okay, because this is a single datum axis because you are dealing with the two circles sharing the same center, yeah, see that. So therefore they have equal importance. So therefore we can combine the entire and put it, if you have a single control frame, you can put it in a same cell, yeah. Of course, in this example, we don't have the frame, yes. So we have no idea where, yes, the tolerance zone is. So anyways, but we do have the basic dimension that you can trace, yeah, all the way to your datum targets. So here we can see the targets are, and so now we can be able to see the targets. Yeah, it's right here, 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 and then here. This is a pretty bad slides. So anyway, so you can see the datum A and then B is right here, sharing that, yeah, center right there. Okay, so two makers of tolerances is going to be used in this, yeah, absence of the specifications. So our basic dimensions are right here. I can see it, but it's okay. Some value is right in there. Yeah, we don't need to care about the value right now. We're just concentrating on the datum target points and how to be able to identify the single datum axis. Okay. All right. The secondary datum axis, regardless of feature size, you can establish that from a set of 3, again, equally spaced target points, yeah, on a secondary cylindrical datum feature, your RFS, in relation to your primary datum surface. So let's get back into this. Okay, we have different views right there. So this time we can be able to see the target points right there very clearly, and they go in order in different views, which is the site. Okay, this is your front. And of course you have basic dimensions right there, yeah. So your datum axis B is going to be right here, yeah. You have your 3 targets, and then they are right here, and then right here, yeah. And then of course you also have the primary, yeah, 3 different points. So you have B and then you have A. So A3 and B3 all together. Yeah. Alright, then circular target lines in cylindrical target areas. You can use it to establish your datum axis. So let's take a look at it. So here we have cylindrical datum target area right there. Yeah. And don't forget, like, there should be, the boundary should be the phantom line. Okay, the drawing is really bad in this slide. And then put your section line, and here is your line, datum target lines right there. So here you can see the circular target, okay, circular target lines and cylindrical target area, that's right here, and to establish your datum axis, right, on the rotating parts. So that's your cylindrical datum target area, and here is your circular datum target line. If you can spot it, you're pretty good, yeah. Alright, then the next few slides, you're gonna have our usual self-evaluation stuff that you have to do, yeah, problems 61 and 63 in your book, so make sure you do that. Choose 3 of them, yeah, to show me that you at least do the assignment and upload it. Okay, so here they are the answers, yeah? And you also have this one, so make sure you at least do that. So there's a problem 61, okay, and then here is your 62, yes, 63, 64 answers, yeah, are all in there for you. So choose 3 of them and do it, please. Alright, some of you are skipping them, okay, I don't know. So we have only 5 more weeks, so make sure you study, yeah. Alright, that's it for today.